Now we're going to talk about vectors. Let's say we're taking off from St. Augustine Airport down here and heading to Jacksonville International up here. And so let's say we took off and here's our airplane and we're pointed directly towards Jacksonville International Airport. But let's say there was a wind at altitude coming from this direction. What would happen if we just pointed our airplane just directly towards Jacksonville International? Well, we would start to shift off to the right. So we would shift off here and then we would have to adjust our heading again towards the airport. But then again the wind would push us over, so we would end up making this kind of arced flight path like this. So to counteract that, we would actually have to point our airplane to the left, and then if we did that we could go straight there. And so in flight planning, that's what we actually do, is we'll look at what the winds are supposed to be like at altitude and then adjust our heading based on that. When we come into land as well, it's important to take a look at the winds and how they match up with the runway. And so if they're not lined up with the runway, there can be a certain amount of crosswind, and this chart here will help us figure out how much headwind there is, how much crosswind there is, and we can determine if it's safe to land. When we talk about values that we have in this class, we're going to have two types of quantities, and it's important to know these two. We have vectors that have to have both magnitude and direction. Displacement's an example. You have to have direction with displacement. With velocity, you must have direction with velocity. Acceleration as well. So there will be values throughout this year that will be vectors. Now scalars have magnitude only. So there's quite a few scalars that we've looked at so far. Position, speed, there's no direction. Time, there's no direction. Mass. We could have density, volume, anything that does not have direction is a scalar. Okay, so when we're drawing vectors, we can notate vectors either by having an arrow on top or by having a bold-faced letter. Sometimes usually I'll just write a vector. We've actually done this where we have a car and here's the velocity vector. We'll just designate what the vector is. And the vector has a tail and a head, and it's a straight line, as you can see here. So this is vector R. And as we draw vectors, they'll always be a straight line. Okay, in terms of direction of vectors, we have to define the direction based on a given angle, and that's what this tutorial is mostly going to focus on here. So the angle is going to be between 0 to 90 degrees, and for instance here, if we have the positive x, we can draw the rest of the coordinate axis here, negative x, positive y, negative y. We had a certain vector based on an angle, we could describe that. But if we just had that angle, we don't really know beyond that, which side of the coordinate axis it is. So it's important to distinguish that. Okay, so now what we're going to do is take a look at an example. Let's say we have a displacement of 10 meters, 35 degrees north of east. So go ahead and first draw a coordinate axis, the north, south, east, west. Okay, and the way this works, and this is probably the most important in the lesson, is we have these here that describe where the angle is. And this is the most important thing, is this location is where you start, and this is where you go. It's very easy to get these mixed up, so this is a really important key idea. So if we start on east, that's where we're looking at here on east, and then we go north, so we're going up north by 35 degrees. So this angle here is 35 degrees. So we start with the second blank, and then we go with the first blank. Okay. Okay. So this is also important as well. We can describe this based on the other way. There's two ways to describe each vector. So in this case, north is where we start, east is where we go, and we go, so we start on north here, north, south, east and west. So we start on north and then we go east by 55 degrees. So this is 55 degrees. So this is actually the exact same vector as the other one. It's just described differently. So the vector here is the exact same as we had before. Okay, so now I want you to try this next one. This is a velocity vector. You draw it the exact same way, but now it's just representing a velocity. And what I suggest is, as you write this out, make sure you got your coordinate axis, north, south, east, and west, and write down what this means in terms of, this is where you start, this is where you go, and then go ahead and draw it out. So go ahead and pause it. Pause the video here and then draw it out and see if you get it right. Okay, so let's see how you did. You start on west and then you go south by 33 degrees. Okay, now we can try this one. This is an acceleration vector. Again, you draw it the same way. It's just this is representing a acceleration. So go ahead and try this one, and pause the video, and then you can see how you did. Okay, so let's see how you did here. So north, south, east, and west. And in this case, we start on north and we go west by 10 degrees. So this is 10 degrees here. Okay, now what I want you to do is describe this based on the other angle. So describe this based on this angle. So what's that angle? We know this is 90 degrees. So what's that angle here? So put that here, and then you can put, where you start and where you go. And so go ahead and pause the video again and then restart it, or hit play when you're ready to check. Okay, so this is 80 degrees. And then we would start on west and then go north. So we start on west and go north. Okay? So in terms of vectors, the magnitude of the vector is based on its length. And so let's say we had a velocity vector that represented 10 meters per second. If we had a 5 meters per second vector that was to the right, it would be half as long. Sometimes our vectors will be to scale, sometimes they won't, but it's helpful usually to have it to scale, and so you can describe things or draw things out the way they are. So again, the vector is proportional to the size that it represents.